Every jet produces noise. Let us have a look at the noise spectrum. For example, in the case of an underexpanded jet, it looks like this. You can distinguish a continuous spectrum, partly due to turbulence, and a harmonic set of discrete frequencies. This is the dominant frequency, the first harmonic, the second harmonic, the third, the fourth, etc. Settling chamber with a reservoir pressure PS and temperature TS, and with ambient conditions PA and TA. At room temperature and given nozzle geometry, the dominant frequency is related to the pressure ratio as shown in this graph. We shall restrict ourselves now to a pressure ratio of 3.4, which for several reasons is a convenient choice. The dominant frequency is then 20,000 Hertz. Now we anticipate two things. In the first place, this dominant frequency is inherent to some periodical behavior of the jet. And secondly, the stability and the discreteness of the dominant frequency suggest an efficient feedback mechanism. So our interest was directed to two questions. In the first place, what is the overall picture of the periodic behavior of a two-dimensional jet? In the second place, what is the feedback mechanism, or at any rate, how is feedback effectuated? Photographic techniques can give an answer to these questions in an exclusive way. As a method of observation, shadow technique gives the best overall information in this case. A single flashlight source, flash duration of 10 to the -7th second, the nozzle, and the film. What does a shadow picture show us about our two-dimensional jet in case the long axis of the nozzle outlet lies in the direction of view? First, the flow field. You can see the nozzle exit, the cell structure, shock waves, and the boundary layers. The turbulent structure is well discernible. In the sound field, these cylindrically outgoing sound pulses are most striking. The distance between two pulses is equal to the wavelength which corresponds to the dominant sound frequency picked up by a microphone and measured by a wave analyzer. From the photograph, the location of the source of sound can be determined. Lastly, the phase difference between sound waves going out on the left and those going out on the right. From a comparison of single shots taken at random, it is concluded that the successive cells move. Here we have a shadow picture which has been exposed twice with an interval of half the period time. It is seen that the successive cells oscillate and that there exists a correlation between this oscillation and the generated sound of 20,000 Hertz. The next step to get more information on the phenomenon is to make a film at a speed of, say, 1 million frames per second. This film can be made in three different ways. One, by means of a rotating mirror camera. Two, by a Kranz-Schardin type camera. And three, by joining in time successive single flash pictures. Although mirror cameras and Kranz-Schardin type cameras give excellent time resolution, both systems have several drawbacks, for instance, non-optimal image quality. The only way to get good spatial information, as well as good time information, is to make a film built up from single shots and using as a trigger the sound pulse of the dominant frequency. Here you see the block diagram, with here the optical axis, light source, nozzle, and film. Then there is also the microphone, which picks up the sound spectrum. The dominant frequency is selected by the wave analyzer and fed into the oscilloscope, and this supplies the step-by-step delayed trigger for the light source every 1/50th of the period. In order to obtain the necessary stability over a period of at least 10 minutes, great care was taken to keep the variation of the pressure at under 0.01 kilogram per square centimeter, and that of the temperature at less than 2 degrees centigrade. Further, the elimination of unwanted aerodynamical and acoustical influences was required. This implies that nearby obstacles are covered with sound-absorbing material, and for the nozzle, a sharp edge and 60-degree cone. The waves reflected at the nozzle wall cannot reach the jet again. Now, let's have a look at the resulting film. You can clearly see, in the first place, the oscillating nature of the jet. In the second place, that the sound is generated at the end of the third cell. To illustrate the accuracy achieved, we made this graph of the sound wave versus the shot number. Shots were taken with an effective time interval of 1 microsecond. The relation between sound and flow field is evident from this film. To obtain more detailed information on this relationship, which may reveal the feedback loop at the same time, experiments were carried out as follows. If the feedback loop lies partly outside the jet, it seems reasonable to assume that the sound pulses themselves convey the feedback signal. To verify this supposition, reflectors were placed outside the jet, taking care not to influence the jet aerodynamically. No remarkable variations were noticed, except when the reflectors were placed against and perpendicular to the outer wall of the nozzle. When we move the reflectors, the oscillation frequency changes as shown in this graph. On the vertical axis, the frequency F is plotted, and on the horizontal axis, the displacement D of the reflectors. For simplicity, both reflectors were at every measuring point kept at the same distance from the nozzle edge. In this film, the reflectors are in a fixed position. There we find some remarkable differences from the first film. First, though the frequency is nearly the same, the oscillation is much more intense. Secondly, the source of sound shifted towards the nozzle. And thirdly, vortices spring up on each side of the jet close to the nozzle and are carried downstream in the boundary layer. We now show the two films again, one without reflectors, the other with reflectors. The following model gives an explanation of what we have seen. Suppose somewhere in the jet a sound pulse is generated which expands cylindrically. Part of this sound pulse is reflected by the reflectors. When this part of the pulse passes the nozzle edge, a vortex develops, or in case of an existing vortex, it is enlarged. The vortex is swept along the cell boundary and its size increases. This process may be regarded as mechanical amplification. At a third cell, a sound wave is initiated by the vortex. Thus, this model contains an acoustical feedback and a mechanical amplification. In this picture, the parts of the feedback loop L1, L2, and L3 are defined. If a sound pulse of discrete frequency F is generated in this way, a relation must exist between the feedback time tau and that frequency. Since the feedback loop must contain a whole number of wavelengths, we may write tau is n over f, where tau is the time necessary to pass once through the feedback loop, and n is any integer larger than or equal to 1. The total time tau t consists of several portions. Tau 1 is the time needed by the sound pulse to travel from its source to the reflector and back to the nozzle edge. Tau 2 is the time necessary to generate a vortex at the nozzle edge. Tau 3 is the time needed by the vortex to reach the original sound source. Tau 4 is the time of interaction in which a new sound pulse is generated. Tau 1, Tau 2, Tau 3 and Tau 4 were deduced from the photographs. Tau 2 and Tau 4 were found to be of the order of a microsecond. Tau 3 equals L3 over C asterisk. We assumed that the location of the source is independent of the location of the reflectors. It was found that the vortex moved downstream with approximately 2/3 of the sound velocity in the ambient medium. So L3 is constant, and C asterisk equals approximately 2/3 C. Adding Tau 1, Tau 2, Tau 3 and Tau 4, we obtain L1 plus L2 over C plus Tau 2 plus Tau 4 plus L3 over 2/3 C equals N over F. If the reflectors are moved, the only changes are in L1 and L2, which in turn causes a variation in F. So we may write We now make a graph of the frequency versus the location of the reflectors for n equals 2, n equals 3, 4, etc. In this graph, the lines are predicted by theory. The dots represent the measurements. It is seen that the theory fits the facts, and we may conclude that the feedback model gives a possible solution. In the first film, we saw an oscillating jet without reflectors. In that case, the downgoing waves initiate vortices which are hardly to be seen. However, these vortices also get sufficient amplification further downstream. In this case, the jet is stable over at least 3 cells. We have shown evidence for the existence of a feedback loop both in the case of the natural screech and in the forced screech with reflectors. Now, if there does exist a feedback loop which lies partly outside the jet, one must be able to interrupt this loop, resulting in a suppressed screech. Now, more cells are stable, non-oscillating. No sound waves are visible. No discrete frequencies appear in the sound spectrum. Conclusions. The photographic study gives a sometimes exclusive answer, either quantitative or qualitative, to the following parts of the problem. A, correlation between the flow field and part of the sound field. B, time schedules of sound waves, vortices, oscillating shocks, oscillating cells, etc. C, left-right phase relation. D, where to find the feedback loop and how it works inside and outside the jet. E, the phase relation throughout the loop. And F, suggestions where to find the necessary amplification and its nature. The problem of the screech cannot be solved by photographic means alone. Complementary methods are still necessary, for instance, to close the amplitude loop. But for the other measuring techniques, the photographs give the most interesting spots, both from a spatial and a time point of view.